Hello students, myself Anna Sahib Gorane, RBNB College Srirampur. Today we are going to study compound microscope from chapter optics of the 11th science. In the previous lectures you have studied about simple microscope. Simple microscope is a convex lens having short focal length and small size. If object is placed within its focal length, its virtual, erect and magnified image is formed on the same side of object. We know this. And we also know the magnifying power of simple microscope. For simple microscope, its magnifying power is inversely proportional to its focal length. For the smaller focal length, magnifying power is large. It means to increase its magnifying power, the focal length of convex lens must be small. And for small focal length, the lens is thick. And for such thick lens, spherical and chromatic aberrations are dominant. So there is aberration. That is the defect in the image formed by the lens if the lens is very thick. And to get the large magnification without causing defect in the image, compound microscope is used. In simple microscope we use only single convex lens. To get the large magnification without defect in the image, compound microscope is used, but this compound microscope consists of two convex lenses. Two convex lenses are there in compound microscope. One is called as objective, denoted by O, having small size and small focal length. This convex lens is called as objective. Size of the objective is small. Focal length of objective is also small. The other convex lens is called as eyepiece, denoted by E, having large size and large focal length. Large size and large focal length. Such two convex lenses are used in the compound microscope. These convex lenses are fixed in a suitable cylindrical tube, and the distance between these two can be changed. They are fixed in a fixed tube. The distance between these two lenses can be changed. So this is the compound microscope. Now we see the image formed by the compound microscope, and then we find its magnifying power. The image formed by the compound microscope is shown in this figure. See here. This is the image formed by the compound microscope. This ray diagram. Here, object, this small size and small focal length convex lens is objective, denoted by O. This convex lens having large size and large focal length called as eyepiece. They are fixed in a tube. The distance between these two lenses can be changed. This object AB is placed just beyond the focal length of this objective O. This object AB is beyond the focal length of objective O. Its real, magnified and inverted image A1, B1 is formed on this side. The eyepiece is adjusted such that this A1, B1 is within its focal length. We can adjust the eyepiece such that this A1, B1 will be within its focal length. So this eyepiece acts as a simple microscope. because we know in simple microscope object is within the focal length. This eyepiece acts as a simple microscope and it produces the virtual, erect and magnified image of this A1, B1, that image is A2, B2. This A2, B2 is the final image of the object AB, and this eyepiece produces the image of this A1, B1. The image is virtual, erect and magnified, and it is on the same side of the object A1, B1. For this eyepiece, this image of the object AB, this image acts as an object. Now here, this UO is the object distance for objective. Its image is here, so this VO is image distance for the objective O. For this eyepiece, this A1, B1 is an object. So this is object distance for the eyepiece. UE is object distance for the eyepiece. And the distance between these two lenses is capital L. That is the length of the compound microscope. We call it as the length. And obviously, from this figure, this length of the compound microscope is VO plus UE. That length is VO plus UE. Beta is the visual angle made by the image at the eyepiece. Beta is the visual angle made by the image A2, B2 at the eyepiece. So this is the image formed by the compound microscope. If object is seen directly without using the lens, suppose this object is AB and we see this object without using the lens, its observed size is maximum at distance of distinct vision. Suppose we see this object from this place. Here there is I and this angle is alpha. And this distance is DDV. That is the distance of distinct vision. If object is seen directly without using the lens, we know its observed size is maximum at DDV, and this object subtends visual angle alpha at the eye if object is at distance of distinct vision. Now see here, from these two figures, if angle is very small, we write it as tan beta is nearly equal to beta, or tan alpha is nearly equal to alpha, and the magnifying power of this compound microscope is, it is also called as angular magnification. It is the ratio of visual angle of image to the visual angle of object. Visual angle of image, that is beta, to the visual angle of object, that is alpha, if object is at DDV. That is, this magnifying power of the compound microscope is beta upon alpha. But from the figure, tan beta, we write it as only beta if angles are small. This tan beta is A2B2 upon VE. That is the image distance for the eyepiece. A2B2 upon VE, or it is also equal to A1B1 upon UE. Suppose this is our equation number 2. From this second figure, tan alpha, that is nearly equal to alpha if angles are small, and that is AB upon D. Suppose this is our equation number 3. We get the value of beta and alpha. Substitute these values in the magnifying power equation or angular magnification, that is equation 1 becomes, our equation 1 will become magnifying power or magnification M is beta upon alpha. Beta is A1 B1 upon UE divided by alpha is AB upon D. AB upon D. Our next step will be magnifying power A1 B1 upon AB into D upon UE. Suppose this is equation number 4. A1 B1 upon AB into D upon UE. But A1 B1 upon AB is equal to VO upon UO. A1 B1 upon AB is equal to VO, image distance for objective, upon object distance for objective. A1 B1 upon AB, that AB, A1 B1 upon AB is equal to VO upon UO. VO upon UO, and that is MO. It is called as linear magnification for objective. Linear magnification for objective. By the definition of linear magnification for objective, this A1 B1 upon AB is equal to VO upon UO. We denote it by small mo, and it is the linear magnification of objective. Also this D upon UE, this is ME. D upon UE is ME, and it is magnifying power of eyepiece. Magnifying power of eyepiece. Hence our equation 4 becomes magnifying power of compound microscope as capital M is equal to MO into ME. What is this MO? VO upon UO, linear magnification for the objective. What is ME? Magnifying power of the eyepiece, and from equation 5 we get magnifying power of compound microscope, or this is the expression for magnifying power of the compound microscope. Now from figure, length of the compound microscope is the distance between objective and eyepiece. This is objective and this is eyepiece. This length is L, and from figure, that length of compound microscope is VO plus UE. What is VO? Object distance for the objective. What is UE? Sorry, what is VO? It is image distance. This VO is image distance for objective What is UE? It is the object distance for the eyepiece, and addition of these two gives the length of compound microscope. Now we see one numerical based on this compound microscope. The numerical is very simple and it is based on this formula. Focal power of eye lens of compound microscope, focal power of eye lens, that is eyepiece, of compound microscope is 6 diopter. That is the focal power 6 diopter. Full stop. The microscope is to be used. The microscope is to be used we use this microscope is to be used for maximum magnifying power, for maximum magnifying power. For maximum magnifying power. It is also called as angular magnification. Angular magnification of at least 12.5. Of at least 12.5. The packing instructions demand that the packing instructions demands that length of microscope should be 25 centimeter. Length of microscope should be 25 centimeter. Determine minimum focal power of objective. Determine minimum focal power of objective. Minimum focal power of objective. Full stop. How much will its radius? How much will its radius, that is the radius of curvature, how much will be its radius of curvature, be if it is biconvex lens, it is biconvex lens of refractive index 1.5. So this is the problem or numerical based on the compound microscope, and it is given that length of that telescope is or microscope is 25 centimeter. So power is given and that is 6 diopter. So given power of the eyepiece, that is 6 diopter, and we know power is given 6 diopter, then magnifying power 12.5, that is M is 12.5, capital M. This 12.5 is also given. Length of the telescope is 25 centimeter. This is also given. Refractive index is 1.5. These are the given quantities. 12.5, L is 25, N is 1.5. Now power of the eyepiece is 1 upon its focal length. Hence F is focal length of eyepiece is 1 upon that power of eyepiece, that is 1 upon 6, and this focal length we know it is in meter, that is 0.1667 meter. 0.1667 meter, or it is 16.67 centimeter. 16.67 centimeter. Now magnifying power of eyepiece we know ME, it is 1 plus D upon FE. ME is 1 plus D upon FE. But we know distance of distinct vision for normal human eye is 25 centimeter. So it is 1 plus 25 upon 16.67. By solving this, we get 1 plus 1.5. This part is 1.5, and that is 2.5. We get this ME, magnifying power of the eyepiece, as 2.5. This is our intermediate answer. But we know capital M is equal to MO into ME. We know this formula. Capital M is equal to MO into ME. Capital M is 12.5 is equal to MO, and this ME is 2.5. Therefore, this MO is 12.5 upon 2.5, value of MO, and that value is 5. But this MO we know it is VO upon UO. Suppose this is equation 1. Capital M is equal to MO into ME. Substituting the values we get MO. That is the magnification produced by the objective. That value is 5. And this MO we also know it is VO upon UO. Now, lens formula for eyepiece is 1 upon FE for eyepiece is equal to 1 upon V minus 1 upon UE. We know lens formula as 1 upon F is equal to 1 upon V minus 1 upon U. But for eyepiece, we write the suffix E. 1 upon FE is equal to 1 upon V minus 1 upon UE. But FE is 16.67. So 1 upon 16.67 is equal to 1 upon V for maximum magnifying power. V is 25 centimeter. That V is 25 centimeter, but it is towards the left side. So it is minus 1 upon 25. Minus 1 upon 25 minus 1 upon UE. 1 upon 16.67 minus, hence we find this 1 upon UE as minus 1 upon 25 minus 1 upon 16.67. This 1 upon UE take minus as a common, 1 upon 25 plus 1 upon 16.67. That is the 1 upon UE. So 1 upon UE is equal to minus sign in bracket 16.67 plus 25 divided by 25 into 16.67. This is the value of 1 upon UE. Negative sign is there. That addition is 41.67. And the multiplication in the denominator is 416.75. By solving 416.75. So this 1 upon UE is equal to minus 1 by 10. 1 upon UE is equal to minus 1 by 10, and hence that UE is 10 centimeter. Minus 10. We get the object distance for the eyepiece as minus 10 centimeter. Now we know length of the compound microscope as we know L is equal to VO plus magnitude UE. That is the length of the compound microscope. So 25, L is 25, it is given. It is equal to VO plus 25 is equal to VO plus that UE is 10 by taking its magnitude. Hence this VO is 25 minus 10, that is 15 centimeter. VO is 25 centimeter. Value of VO, we get it as a 25 centimeter. But from equation 1, VO upon UO is 5. From equation 1, VO upon UO is 5. Hence UO is VO upon 5. But what is this VO? It is 15 upon 5. We get this UO as 3 centimeter. We get the value of UO as 3 centimeter. Now similar to eyepiece, we also write lens formula for objective. For objective, this lens formula is 1 upon FO is equal to 1 upon VO minus 1 upon UO. Substitute the values. 1 upon VO, that is 15. 1 upon 15 minus, but this is minus, so minus 3. This is 1 upon FO. 1 upon 15 minus 1 upon 3, that is 1 upon 15 plus 1 upon 3. 1 upon FO is 3 plus 15 upon 15 into 3, that is 45. 1 upon FO is 45 upon minus 3. 15 plus 3, that is 18 upon 45. Hence FO is 45 upon 18. FO is 45 upon 18, and that value is 2.5 centimeter. focal length of the objective is, we get 2.5 centimeter, or it is 0.025 meter. From this formula we get the focal length for the objective. Here we use lens formula for the objective. So focal power of objective is 1 upon FO, and this focal length is in meter. 1 upon 0.025, and hence focal power of objective we get, it is 40 diopter. This is our first answer. Focal power of objective is 40 diopter. Now we know lens maker's equation, 1 upon FO is equal to n minus 1 upon R1, that is R, having the same radius of curvature, minus 1 upon R2, but this is minus, one radius of curvature is positive, other is negative. So we write 1 upon FO, that is 2.5, is equal to 1.5 minus 1 in bracket 1 upon R plus 1 upon R. This is 1 upon 2.5. This is equal to 0.5 into, this is 2 upon R. 0.5 into 2 is 1, that is 1 by R. 1 upon 2.5 is equal to 1 by R. Therefore, R is 2.5 centimeter. This is our second answer. We get the two answers. This radius of curvature of the convex lens is 2.5, and the power of that objective is 40 diopter. By using the formulae related with that compound microscope, we find these two answers. Okay, today we stop here. Thank you.